In this section, we are going to discuss about I/O read and I/O write machine cycles of 8085 microprocessor. The I/O read cycle is executed by the processor to read a data byte from I/O port or from peripheral device. In order to complete I/O read cycles, it requires 3 T states. The in instruction uses this machine cycle during the execution. Corresponding to I/O read, the status signals are I/O by M bar is equal to 1, S1 is equal to 1 and S0 is equal to 0. It is to be noted that the port address width is only 8-bit. So, both address bus and address data bus carries 8-bit address during first clock cycle. Address bus carries this port address during remaining clock cycles also. But in the case of AD bus, we need to make it free during second and third clock cycle. For that, we can have a demultiplexing process by means of ALE signal. ALE signal goes high and suddenly goes low during first clock cycles of every machine cycle. During second and third clock cycle, address data bus is free. So whenever RD bar signal goes low during second clock cycle, data from the port address is placed in address data bus. And during third clock cycle, when RD bar signal goes high, now the data is available in data bus, that is transferred to microprocessor, that is CPU. Let's see the graphical representation of this operation, that is timing diagram corresponding to I/O read machine cycle. Similar to earlier case, first of all we need to draw clock signals like this. Then, as we discussed earlier, both address and address data bus carries I/O port address during first clock cycle. During second and third clock cycles, address bus carries I/O port address. But in the case of AD bus, we need to make it free during second and third clock cycles. So ALE signal is used to latch this port address, which is available in AD0 to AD0 during first clock cycle, so that this I/O port address is available during second and third clock cycle as the output of this external hardware. So ALE signal is going to high and then going to low during first clock cycles of every machine cycle. And this is the status signals. I/O by M bar is equal to 1, S1 is equal to 1 and S0 is equal to 0. Now data bus is free. Wherever RD bar signal goes low during second clock cycles, the data which is pointed by this address, I/O port address, that is transferred into this address data bus. And whenever RD bar signal goes high during third clock cycle, the data which is now available in this bus, that is transferred into specified registers in microprocessor. So in this way, we can draw the I/O read machine cycle timing diagram. Next one is the I/O write machine cycles of 8085 microprocessor. I/O write machine cycle is executed by the processor to save a data byte which is available inside microprocessor to I/O port or to peripheral device. Similar to I/O read, in order to complete this machine cycle, it requires 3 T states. Corresponding status signals are I/O by M bar is equal to 1. Why? Because this address is related to I/O device. Therefore, I/O by M bar is equal to 1. S1 is equal to 0 and S0 is equal to 1. So this is the timing diagram corresponding to I/O write machine cycle. Similar to earlier case, we need to draw the clock signal like this. As the port address width is only 8-bit, both address bus and address data bus carries port address during first clock cycles, and address bus carries this port address during second and third clock cycle. With the help of ALE signals, Along with the D-latch, this port address is make it available during second and third clock cycle also. So that process is known as demultiplexing. For that, ALE signal suddenly goes high and then goes low during first clock cycles of every machine cycle. And this is the status signal. As the address is related to IO device, IO by M bar is equal to 1, and corresponding to write operation, S1 is equal to 0 and S0 is equal to 1. During second and third clock cycle, AD bus is free due to demultiplexing process. So whenever WR bar signal goes low during second clock cycles, the data which is available inside MUP is placed in this AD bus, and whenever WR bar signal goes high during third clock cycle, the data which is now available in AD bus is transferred to this port address. So next important thing is ready line and wait state. Ready signal is an input signal to microprocessor used to slow down peripheral operation. Ready input signal is used to slow down the processing. During first T state of a machine cycle, MUP places address of peripheral device on address bus and address data bus. Low order address is handled by AD bus and higher order address is handled by address bus. If device is not ready, it will return a low ready signal. During T2, MUP check ready line. If ready line is still low, MUP enters a wait state. Again it check ready line during wait state. If line is high, MUP goes to third T state. If it is low, MUP again enter to another wait state. Thus, wait state introduces between T2 and T3 until peripheral device become ready for data transfer. Let's see a memory read machine cycle with one T state. Here, this is the clock signal. During first clock cycle, program counter places higher order address on address bus and low order address on AD bus, and ALE signal goes high and suddenly goes low, and status signals are IO by M bar is equal to 0, S1 is equal to 1 and S0 is equal to 0. Whenever RD bar signal goes low during second clock cycle, as data bus is free, the data which is pointed by HOA and LOA is transferred to this AD bus. If the device is not ready, it will return a low ready signal. Here we can see a low ready signal is coming from T1 onwards. So during T2, MUP will check the status of ready signal. It will check whether this ready signal is low or high. When it is low, it will enter into a wait state. So during wait state, whatever be the condition available in T2, that is retained. Again during T wait, it will check the status of this ready signal. Whenever this ready signal is high, it will enter to T3. If this ready signal is still in low condition, it will enter to another T wait. So whenever this ready signal goes high, then only it will enter to new T state, that is T3 in this case. So in this way, slow peripheral can be connected to microprocessor by means of ready signal.